We'll just finish 12.3, and then if there's any homework questions, um, sort of talk about those as part of the review. So, okay, so we were looking at the derivative or equation of tangent line. Um, Remember, this is our formula for the derivative in polar coordinates. You can choose to remember the formula, or you can just parameterize. Either way, it's the same thing. I just don't think that's really intuitive to try to remember, but I guess you can memorize.
I mean, couldn't you just plug that the R in, and just take the derivative that way instead of having to memorize that?
Yeah. So that's what we're doing here. We said that our function of theta is r1 minus sine theta, and we said since y is r sine theta, then we're just having our r times sine theta for y, and then our r times cosine theta gives us x. So then when we look at the derivative, we don't really have to remember the formula. We could just take the derivative of x, the derivative of y, and then divide them to get the derivative.
dy on top, right?
Yeah, right. Otherwise, we put our r in here, multiplied by cosine, plus the derivative of r times sine, that whole stuff. So, anyways, that's the route we're taking. Okay, so our y was sine minus sine squared, and our x was cosine minus sine cosine. All right, so then our dy over dx, which is really just y prime over x prime with respect to theta. So I think I'll just write this one more time. The derivative of y with respect to theta over the derivative of x with respect to theta. And then from here on out, I'll just say dy over dx. So we take the derivative of y, derivative of sine is cosine, minus the derivative of sine squared, which is 2 sine theta cosine theta. So should we write that here? And then our x prime, we'll write that here, minus sine theta, minus the derivative of the product, that's sine minus cosine, plus sine squared, and we have minus sine times derivative of sine plus cosine, so we have minus cosine squared. So there's our x prime. So all of that quotient represents the derivative. Given any theta, how do we measure the slope at a particular point on the cardioid? Yeah. So notice it's a function of theta. So all we need is to find the slope at that point. R theta, we just need our theta. This is our R, this is our theta. So sometimes the notation, you'll see this vertical bar, theta equals to pi over 6. Yeah. Theta equals pi over 6. Just means we're evaluating the derivative at a theta value of pi over 6. Just to save some space. All right, so what do we get? Yes, that middle thing at the top is totally busted. Okay, cosine of pi over 6 minus 2 times sine of pi over 6 times cosine of pi over 6. Oops. And
It's just zero. Right?
that's just 0. So now we just have to make sure that the denominator is not 0 and we're good. So minus 1/2 plus quarter minus 3 over 2 minus those. So that's not 0, is it? So the slope of the tangent line, the slope of the tangent line on our cardioid at the point 1/2 pi over 6 is 0. And we can sort of verify that from the graph itself, that we have a horizontal tangent.
At zero?
No, at the point 1/2 comma pi over 6, which is that point right there. So it checks out. Now, a lot of times the graphs aren't provided, but in a lot of instances they're like really helpful when you're doing derivatives or areas, especially areas. Anybody have any questions on this?
How do you determine if this is
So I should cover this last one, but I just want to do a little reminder. So when we initially derive it, so when we say that y equals r sine theta, f of theta sine theta, so the function of theta, why is that 1 minus sine theta, or when you plug it in for the axis, it's 1 minus cosine theta? Out of curiosity.
So say the second part again.
So why is when you're trying to derive it, so the function of theta sine theta for y, why does the function of theta 1 minus sine theta?
Oh, because that was given to us. That's this function right here that describes that cardioid.
But then and we're just multiplying it by sine theta because it's the y.
Yeah, right.
Okay,
Yeah.
sure.
Right. This is y equals to r times sine theta, where r is a function of theta. So it's like it's backward because we write the point r theta in polar versus like x y, which is really x comma f of x. Right. So this is really this one in polar is the coordinates are kind of reversed as what's intuitive for independent variable, dependent variable. But this is f of theta, comma theta. So even though it's like thetas are independent variable, it's still by convention r theta for describing a point. Any other questions? What were you gonna ask, Drake? All right then. So I meant to put these down, but find the slope of the tangent line at of 2 sine 3 theta at the tip of the leaves, and let me just write down the tip of the leaves. Occur at pi over 6, at 5 pi over 6, and at 3 pi over 2. Remember, the derivative is a function of theta. Technically, we just need a theta value to compute the slope. All right, so why don't y'all compute the derivative? Just for time purposes, we'll evaluate these quickly. Let's all see if we can come up with the derivative. Depending on how you write this out, yours might look a little bit different than your neighbor's, so just keep that in mind.
That's what I was just, yeah.
No one responded.
No, that's, I like get where you're going.
I never said I knew what I was doing. Yes.
I like kind of holds my pants
How does he not be as smart as Isaac? Literally, he's only 15.
I was like, so fucking
That's not how you do it. Yeah. Why do you?
That sounds right.
I know, I remember.
Oh, no, no, wait.
Right.
Yeah.
It's interesting how this has to vary.
Yeah, I'm not sure what the delay is. Okay, so you should have came up with that for your derivative. I don't know, some of you were working on evaluating at particular values, so I'll just list those here if you want. Derivative of y with respect to x at pi over 6. Anybody get that?
Negative square root.
Yeah, negative 3. And we can verify here's pi over 6. We have a negative root 3 for the slope of that line. So I think at this point it's not difficult, it's just kind of tedious because the derivative is always pretty complex. What's the next one? 5 pi over 6. Let me do that one. Positive square root of 3. Yeah. Well, on that one we do. Yeah, because the.
If we do that on the exam, is it okay? You're like, hey, this appears to be symmetrical. This other one's not
Yeah.
square root of 3.
Yeah, a lot of times we use symmetry to help out. Well, we have a problem where we actually do that.
Do you need us to write that on the exam by symmetry, or will you just accept that?
I don't know. I hope it's pretty obvious.
Okay, cool.
Yeah. What's the last one?
0.
Yeah, we can totally see that this should be 0. What was that? 3 pi over 2. Okay, any questions on that? Another question they could ask is, given a particular curve, they could ask you to find the slope of the tangent line at the pole. Does anybody remember what the pole is? That was the polar axis, was the positive x-axis. At the origin, yeah. So the pole is just this point here at the origin. What's unique about the point at the origin? Yeah, multiple lines go through it. What else? What else could we say?
Is that where the thing equals 0?
That's where what thing equals 0?
The R.
R, right. That's where R equals 0. Theta can be anything. If R is 0, theta could be any angle measure. You're always talking about the point at the origin. So the pole is always when the radius is 0. Theta can be anything. So to find the slope of the tangent line at the pole, we first need to find the equation of the tangent line at the pole. And in order to do that, what do? Okay, so if we take this derivative, we'll have a dy over dx in terms of theta, right? So what theta do we plug in to find the slope of the tangent line at r equals 0? Okay.
First, we can plug in 0 to find out.
Yeah, so first we have to figure out what thetas give us an r equal to 0. Because remember, what's happening here, I'm not quite sure, but when we plot points, this thing does unfold in a particular fashion. You know, maybe it unfolds like this. So there are multiple instances, I don't know, where it does cross the pole, but it's not at all theta value. So we couldn't just wing it and say, well, maybe at pi over 2 it might cross, right? I don't know. I mean, it looks like it right there, but
So to create the whole structure, though, that's a period of 2 pi, right?
no, because your period is affected here.
Oh, I see.
Yeah.
Okay, then it's pi, and can you divide it by 4 and say? So,
Yeah. Well, it's actually, yeah, the period is actually pi, right?
Right, but then since we have 4 lobes, could you divide that period by 4 after that? After you calculate what the actual period is, and then say those 4 values?
Do what? Say that again? Sorry, I didn't.
No, you're fine. So, okay, so the period is actually 2 pi over 2, which is pi.
Uh,
But we have 4 lobes. You divide, and they're 4 equal lobes. You divide them pi by 4, and you get basically 4 values that you could use at that point. Would those be the correct values?
well, it depends on how they were constructed,
Okay.
right? So what we do know is that if if this curve is intersecting the pole at r equals 0, then this whole thing has to be equal to 0. That's what we do. We set 4 cosine of 2 theta equal to 0. Figure out for what angle measures that shape passes through the pole. Yeah. For what else? Yeah.
Just be pi over 4, 2 pi over 4, 2 pi over 4.
Right?
They're signing for the- I was on the right track.
So here's the thing. We know that the curve crosses the pole at those angle measures, but it says find the slope of the tangent line at the pole. There's more than one tangent line. So if we're looking at theta equals to pi over 4, what is that actually describing? If we say that's an equation that theta equals pi over 4, what is that? The top, what do you mean? Like the
Furthest right, it's the top portion. The tangent line is that top portion.
right here? Do y'all agree? So remember in polar coordinates, lines that pass through the origin have equation of theta equals to theta naught. There's our theta naught. Theta equals theta sub 0. So what is the slope of that line? It's not horizontal. Okay. Not 1/2.
Looks like the y equals x line is the slope line.
Mm-hmm. Yep, so the slope of this line, remember we have to, in order to convert theta equals theta naught, theta equals pi over 4 into, excuse me, Cartesian. We take the tangent of both sides. In terms of x and y, what's tangent of theta? Well, tangent of pi over 4 is 1. What's tangent of theta turn into? Y over x. It is sine theta over cosine theta. But it's also defined as y over x, which means y equals to x. So that's the same as this line right here. It's a slope of 1. The slope of your line is just the tangent of that whatever, the radian. But we know that line y equals x or theta equals pi over 4 isn't just that top portion of the line, right? It's actually all of this. Okay, so that's the slope of the tangent line there, it's 1. What about our next value, theta equals 3 pi over 4? Yeah, so we've got the slope of this line is the tangent. I mean, it just so happens to be the tangent line, but the slope of the tangent line here is the tangent of 3 pi over 4, which is -1.
How do you know that it's a
Do what?
How do you know it's a
Well, that was from 12.2 when we were converting from polar to rectangular. Yeah. So yeah, the conversion gave us some insight into to when we look at a theta equals to something, how we tell what the slope is. So we don't really have to necessarily convert it into like y equals to x, because the slope of the line actually came from this part right here.
So that would be the slope of the polar portion.
Yeah.
You can't have time.
Right. Right. Yeah. Exactly. Here's the other one here. Yeah, so what happens when we get to a theta value of 5 pi over 4? Yeah. So if you want to look at that, then just compute when theta is 5 pi over 4. Again, the slope of that line is the slope of the tangent line in this case. And the tangent of 5 pi over 4 is equal to 1. What about 7 pi over 4? -1. Yeah, so in fact, we just have these two lines. They keep repeating. Yeah, we'll just indicate that they keep repeating. Same as 7 pi over 4, and so forth. Because those two, pi over 4, 5 pi over 4, are the same lines. 3 pi over 4, 7 pi over 4, same lines. Yeah.
There would be a situation like that. So I guess functions like this that are designed, they'll either be like phase shifted or vertically shifted. How does that change anything?
Yeah.
If it's not centered at the origin.
Right. Yeah. If it's not centered at the origin, then you have a different. You don't have a line passing through the pole anymore. That it's not described by theta equals to something. Yeah, we don't encounter those. At least I didn't see any examples. So really, we just have those two. And the process is the same. If you have any curve and they want to know where the equation of the tangent line at the pole, you set the function equal to 0, solve for those theta values, tangent of the theta values give you your slopes. Right. Now, a similar kind of setup here with horizontal and vertical lines. We're really concerned about finding horizontal tangents and vertical tangents. So slope is 0, undefined slope. But similar to what we looked at in 12.1, we said that the horizontal tangent lines occur when the numerator of the derivative is 0. So the numerator of our derivative is dy over d theta, or y prime, equals to 0. And what else? Yeah. And the denominator dx over d theta, or x prime, is not 0. That's how we locate horizontal tangents. Similar vertical tangents are when dy over d theta is 0. Yeah, dx d theta, thank you. We'll just do this. dy d theta is not 0, and dx d theta is 0. And then, of course, the indeterminate form is when both of them are 0. So when dy d theta is 0 and dx over d theta is 0. We won't look at those. There is an example like in your textbook that does have an instance where it's 0 over 0, and then so you've got to use L'Hopital's rule, the limit as theta approaches whatever value causes 0 over 0. No. All right, so we'll look at this, I guess, a little bit more straightforward of an example, and then we'll look at a more difficult example. So find the points for which we have a horizontal and vertical tangent on our cosine theta. So we can see that's a circle. If we didn't know that's a circle, our cosine theta, what's a way to describe that so we know what kind of circle that is? In other words, the center of the radius. Remember this formula? So yeah, we've got really two things we can remember. We can either remember that r equals to 2 times a cosine theta is a circle with a center of what? A0, and the radius of, yeah. Or we could take the r equals cosine theta and convert that into rectangular coordinates, and then look at that. So it was mentioned that we take our original, multiply it by r. So we have r squared equals to r cosine theta, which is x. And then we can get our similar terms together and complete the square. It's a little bit more long-winded to convert. In our formula 2a cosine theta, what is our a? It's not 0 because then r would be 0. A is 1/2, right? It's the only way to get a 1 right there, 2 times a half. A equals 1/2. This is a circle with a center of 1/2, 0, and a radius of 1/2. Yeah, then you get to complete the square on x. So we take half of the term here. Sorry, half of the coefficient.
X squared minus x.
Oh yeah, x squared minus x, half of the coefficient. So half of -1 is -1/2 squared. We add that to both sides. And that's x minus 1/2 squared plus y squared equals 4. Center 1/2, 0. Radius 1/2. So when looking at the graph, we should see that we have 2 vertical tangents here on the left and right, and 2 horizontal, I guess, top and bottom. So I guess that was just. We've got to first find the derivative. So parameterize, we have r as cosine theta. So y is r sine theta. There's r sine theta. And x r cosine theta. Look at the derivative, y prime. Product rule and x prime chain rule. Therefore, then our dy over dx is minus sine squared plus cosine squared all over negative 2 sine cosine cosine squared. Okay, so that's what we're after. To find our horizontal tangent, we have to look at when the numerator is 0. And honestly, we could probably look at these simultaneously just to make sure the zeros we get for this equation aren't the zeros we get for the denominator. Maybe we should have enough so we can kind of compare them. Okay. So how do we solve then negative sine squared plus cosine squared equals to 0?
You just add sine squared theta.
When sine, well, yeah, so when sine squared equals cosine squared. Or we could divide, say, when does tangent squared equal to 1? I think that's a little bit harder of a problem if we go that route. I mean, we certainly can attempt that if you want. All right, but I think the easiest way to solve this is to remember that this is an identity for cosine squared minus sine squared is cosine of 2 theta. So pi over 4 is one value, but what are the others? Same ones we got in the last problem, right? Yeah, odd power, odd numerators, pi over 4, denominators. Okay, so that's when our derivative is equal to 0. But let's go ahead and make sure that the derivative is not 0, or the denominator of the derivative is not 0 at any of these values. So negative 2 sine cosine. I think that's easy enough to solve because it's already factored out. So either we could say that this is 0 when sine of theta is 0, or when cosine of theta is 0. We know that, hopefully we remember that identity, 2 sine cosine is actually the sine of 2 theta. So this is, we could call that minus sine of 2 theta for 1 and 2. Yeah, I did it too. We use that, I don't know, quite a lot when we did like trig substitutions and stuff. But either way,
Zero,
so yeah, so we've got 0, pi, 2 pi when sine is 0, cosine is 0.
It's every half pi, right?
Yeah. Odd. 1, 3, 5, 7, 9, etc.
oh,
So none of those values are the thetas we had for when our derivative of the numerator was 0. So there's never an instance where they're both 0 at the same time. So nothing weird going on. Now we know when the derivative is 0, we know when the derivative is undefined, and we're asked to find the points for which the tangent line is horizontal. We have the independent variable or the input for when it's horizontal and when it's vertical. So points when theta equals pi over 4, just, you can make a chart if you want, or just plug in each individual one. So we can just generate a table with our pi over 4, 3 pi over 4, 5 pi over 4, or this or that. I don't know if you have a preference, but don't do it this way. Remember the R was defined as, what was it, cosine theta? Okay, so when theta is pi over 4, R is cosine of pi over 4, which is, yeah, root 2 over 2 or 1 over root 2. So we have the point R theta. When theta is 3 pi over 4, cosine of theta 3 pi over 4 is, yeah, negative 1 over root 2. So that point, negative 1 over root 2, 3 pi over 4. Yeah, so it's 5 pi over 4, again, back to 1 over root 2.
Shouldn't be root 2 over 2? Yes, that, if you,
Same
if you
thing.
simplify it down, you like radicalize that expression. It's not-
Yeah, rationalized denominator, same thing. Okay, so let's we had other values, but let's check these, what we have so far. Okay, so what do we know about the point 1 over root 2, or root 2 over 2 comma pi over 4, and root 2 over 2 comma 5 pi over 4. So just think about 10.2 when we had all those polar points and we described those, and then we said come up with an equal representation for the same point. So from pi over 4 to 5 pi over 4, we had to add pi, and then if we add pi, then we negate the r, we have the same point, right? So are any of those the same point? Is what we want. Is kind of what we're thinking about. Wait, cosine of 5 pi over 4 is what? Negative root 2 over 2. because 5 pi over 4 is in the third quadrant.
Yeah.
Okay, so now, are any of those points the same?
Those are the same.
The first and third points are the same. These are the exact same point. So those are the same exact points. So really we have 2 points. What happens if we're looking at theta of 7 pi over 4? It's the same as when theta is 3 pi over 4. So really we even though we have multiple points that come out of this, we should only have 2 horizontal tangents. Okay, so let's just make note that the only points that we get here are 1 over root 2 over 2, comma, pi over 4. And what was the other one? Negative root 2 over 2, 3 pi over 4. Those are for the horizontal tangent. Top and bottom of the circle. Back up to our vertical tangents, we'll do the same thing. R theta. I'll get 0. I guess we'll just go in order on how we listed these. Okay, I mean, I don't know if we need to keep going out more, because really, there's only 2 unique points here. So let's see which ones they are. Cosine of 0 gives us 1, that's a 0.10. Cosine of pi is negative 1, negative 1 comma pi. Is that the same point? One comma 2 pi. Same point as well. Okay, pi over 2, 0 through pi over 2, 0. Right, so all the odd pi's over 2, you're at the origin or the pole again. I'm gonna write the points down. So those are the same points as well. So really the only 2 points that come out of that are whichever ones you like, 1, 0, and 0 pi over 2. Again, looking at those on the graph, here's the point 1, 0. Vertical tangent at the pole, 0 comma 2 pi, vertical tangent. Have any questions on that? So we could probably work this. I just want to mention that at some point you really get to a place where in this problem where you're kind of stuck unless you can make use of the graph. So let's go ahead and graph that. We're finding still where the tangents are horizontal or vertical. So how many places do we have a horizontal tangent? 4, 5, 6. Where's the 5, 6 coming from? Huh? The middle. So we could possibly have a horizontal tangent here. So we have a horizontal tangent here, at the top of the petals, at the bottom, and perhaps through the hole. How many vertical tangents? Same, right? At least we think. Our work can actually justify. So really, the question is would we actually have a vertical and a horizontal tangent at the pole? And it really just depends on how these figures more or less approach the pole as they sort of unfold, right? So it certainly looks like, maybe it comes out like this and then falls into the pole in a vertical fashion. And kind of the same thing, maybe it loops back around and falls back into the pole. It's virtually horizontal right there. But we'll verify that to make sure. Really, the symmetry is utilized because, part of this problem has us taking, we're solving an equation where the cosine or the sine doesn't have a nice value, like pi over 4, pi over 6. So then you have to use a calculator and get an approximation. And then that's when we use the fact that, well, if this has a certain coordinate, this one's when, think of it as x, y for a moment. This is when x is negative and y is negative. This is when x is negative and y is positive, right? Positive, 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 negative. So then we can use that kind of symmetry to get the other points. I think perhaps we'll start this after break, though. It's pretty lengthy. Is that okay? All right, we'll take a break. We'll skip this one. We could talk about now finding area in polar. It's the same notion of when we found areas in rectangular coordinate systems, where we said, here's this region, let's slice it up, see what kind of shapes we make, and then sum up all of those areas of the rectangle. Same principle. So we have some funky region, but this time, things are in terms of r and theta. We're going to slice through it in a particular fashion, which generates, something to this effect. And it's actually the slices generate what? Yeah, they're definitely not rectangles. So here, let's. So then we approximate those areas with sectors. And as we fill that region up with sectors, the more and more we put in there, the more accurate that area gets. So again, slice, sum, let the number of those things go to infinity gives us an exact area. So since we're dealing with, maybe a large one of these, it's kind of that big. So that's just a sector of a circle. The area for a sector is 1/2 r squared times theta, where theta is this angle measurement. And then, of course, r is just the radius. Either there or there. It doesn't matter. Eventually, they get small enough where it's virtually the same. But recall in polar that r is actually a function of theta. So the 1/2 r squared turns into 1/2 f of theta squared, and then each angle measure is kind of like the length of each rectangle in the XY system, where all of those could be different. But the point is as we made those smaller and smaller, they all approached zero. So these thetas are really, yeah, delta theta sub k for each one of these. So here's theta 1, here's theta 2, theta 3, theta 4, theta 5, et cetera, et cetera, et cetera. Okay, so the area then turns into 1/2 f of theta squared d theta, which is how we get the 1/2 f of theta squared d theta. And then the thing we're looking here is a more generic take on that. So think of this formula as it's equivalent to this kind of thing, where we had a function of x and another function of x. We said, what's that area? We had to do the top minus the bottom, or the right minus the left. So this f of theta is larger than or equal to g of theta, which is larger than or equal to 0. So maybe I think in terms of the figures that are generated, it's easier to think about f of theta as the outer, outside or outer curve, and to think of g theta as the inside. But that whole integrand is simply based off of the area of the sector that we're summing up to infinity. Notice alpha and beta, those are angle measures. So like if I want to find the area from 0 to pi over 2, then I'm integrating from alpha to beta 0 to pi over 2. Mm-hmm. Yep. With respect to beta, yeah. So alpha and beta are theta values. Okay, make a sketch and then find the area of the region inside the circle r equals to 8 sine theta. R equals to 8 sine theta has a center and a radius of what? Center of a radius? Yes, with signs, which with y that's getting shifted. It's positive, so that the center gets moved up 4 units. Okay, so there's our sketch. Now, naturally, the easiest way to do this is just calculate the area of the circle. So let's use this to check. Here's our check that the work we're about to do is correct. So the area of that circle is pi r squared. So once we construct the integral and evaluate that, we should get 16 pi. All right, so let's then set up the integral for this. There's a couple of ways we could approach this. Usually utilizing symmetry saves you a lot of effort with these integrals. Yeah.
Okay, so when we're given the integral of this from this theta to this theta, when we're is that from the origin or the center of the circle?
So we have to, that's a good question. You have to look at this and say this circle, try to envision how it unfolds. And if you can't, then maybe you need a table of values. So, we plot a bunch of points and we get that circle. So we can check when theta is 0, r is 0. So that's where we start. When theta equals to pi over 4, when theta equals pi over 2, etc. You can kind of look at that as that's how the circle is unfolding as the parameter of theta increases. So what would our theta values be on the definite integral? Just from 0 to 2 pi, what do y'all think? Or would it just be 0 to pi? Right, so here's a theta value of 0. Here's a theta value of pi over 2. So if we go from 0 to pi over 2, we sweep out half of the circle. Everybody see that? So if we go from pi over 2 to pi, then we've swept out the other half of the circle. Does everybody agree? If you go from 2 pi, then you're going to sweep out the circle once more. So this is a theta value of 0. And I'll just put these here. This is a theta value of pi over 2. So half of the circle is swept out at half pi.
If this was below the x or like in the middle,
Centered at the origin.
Yeah, would that change what we just said?
Yeah. So if this were centered at 0, 0, then maybe we integrate from here. There's many ways we can do it. You can integrate from the polar axis up to this point, but that would just give you a quarter of the area. We could integrate from theta equals 0 to theta equals pi. That would give us half the circle, and so forth. So yeah, it would change. Just imagine theta here starting at 0 and sweeping out your figure. So 2 pi is actually too much here. We just go to pi, we have the whole circle swept out. Okay, and our integrand is 1/2 times the function of theta squared d theta. Notice there isn't two curves, so we don't have an outer and an inner. We just have that one particular curve. Or we can utilize symmetry and say that this is equivalent to twice the integral from 0 to pi over 2, right? So we find half of the area of the circle and then we double it. Not squared yet. So we're all right with that? Yeah, yeah. So and since there's a half built in, if you can utilize especially this double symmetry, that half goes away. It's a little bit easier. Let me just run here. This is the full circle. Half of the circle multiplied by 2. So we see the formula for half, I think personally is a little bit easier. You can take either approach and we'll get the same area. we'll work with the second one, 2 times a half, that's gone. We just need to take the integral from 0 to pi over 2. 64 sine squared. Is everybody all right with that? The setup? All right. So here's the sine squared again. Remember to handle that, unless you just remember what it is, we rewrite that as 1/2 times 1 minus cosine 2 theta. And integrate that way. So we have 32 times the integral from 0 to pi over 2. Integrand is 1 minus cosine 2 theta. Here, so 32, that's theta minus 2 sine 2 theta from 0 to pi over 2. Yeah? All right. That's 32 pi over 2 minus 2 sine of pi, evaluated at 0. We have 32 times pi over 2. 32 divided by 2 times pi. So it checks out with the area of the circle. Anyone have any questions? It's almost like we have to visualize this now in a different way, right? With the XY coordinate system, they were all stopped at some line, and it was easy to tell start, stop. Here it's a little bit more tricky, just by the nature of the theta and how these functions unfold, I guess. All right, so let's try this one. Find the area that's common to the circle, r equal 1. I'll give you a graph on the final, so you'll have the figure that's provided, and the cardioid plus cosine theta. Yeah, the area of the, what is that, a kidney bean? The area of that thing. So we can make this certain computations a lot easier utilizing symmetry and any other facts that seem legitimate from the graph. Looking at a graph isn't always the best approach, but when we're finding areas, it's really crucial, I think, unless you're just looking at circles. So I guess here's how we're going to look at this. Notice that the area common to consists of half a circle. So this area right here is just half of that circle. This area is half the area of a circle. So we can get a bulk of that just by using area of half our circle. Of course, it's a r equals 1, so it's circle radius 1. So that's just equal to pi over 2. And then what we need to add to the area of the circle is the area here and this So that's not as straightforward. There's no, it's not a geometric figure. So we'll have to use an integral to establish that.
That one, we also just do one of them.
Yeah, exactly. So utilizing symmetry here as well, just finding the area maybe of the top portion and then doubling that. So this area, well, let's just set up the integral first. So we're going to look at half of this, which means we need to double our area. And where would theta go? If theta ranges from where to where? Say that again. 0 to pi over 2. What do y'all think? So when theta is 0, you're here. We don't want to trace all of that out. Because if we go from 0 to pi over 2, then theta has to sweep through here, right? Pi over 2 to pi. Does that seem more reasonable? Pi over 2 to pi. Well, sorry, let me get rid of those other ones. So that theta is starting here at pi over 2. And it's, this cusp, we're tracing that out. Theta is pi over 2. Just imagine this clock hand rotating counterclockwise. We're sweeping out this part to here, where theta equals to pi. If you're unsure about that, you can say, okay, well, where does my cardioid 1 plus cosine theta meet the pole? So where does my cardioid go back, intersect the pole again? And then that can give us that theta value. It just kind of depends on where we're at, right? It depends on where that theta is.
From pi over 2 to pi.
Yeah, so from pi over 2 to pi, we have those two. I think those are the easier ones to see. But what about that sector? We're only finding the area that's generated in that red as part of that cardioid. So do we need to do the inner minus the outer? Sorry, the outer minus the inner here? No. What if we did say, let's just talk about this for a second. What if we did look at the integral from pi over 2 to pi, but instead we had 1/2 times, that's our circle, r squared minus 1 plus cosine squared, cosine theta squared. So if we said that's the outer minus the inner, what part of the area, what part of that figure would we calculate? What area would we calculate? Outside of the cardioid, but inside the circle, right? So when we do the outer minus the inner, we're just looking at that segment. So from here to here, from here to here, right? The whole time we're just looking at that area. So you would just get the top half of the circle, the area that's outside of the cardioid but inside of the circle. If we did this one here. Yeah.
Can we choose to fan out from a different point, like at the left side of the circle?
So like if you started here, you mean?
Left of the circle, like the left.
Here.
Yeah.
I mean, you can still find
If you start, is there a way to do that? Wouldn't that be more helpful? Or can you do that?
No, because theta starts on the polar axis,
Okay.
which is connected to the pole.
Gotcha.
Trey, what were you?
So you can still find the area of that. You just need the area of the circle minus that. If you're looking at the polar calculus.
The area of the circle minus the what we have in green, or yeah, so yeah, you would still have to find that though.
Yeah.
But you could, yeah. So we could find the area of the circle here and then subtract off this area in green to get that area in red. But then that would also give us, it depends on how far. If we only took our green out from pi over 2 to pi, then all we would get is this area right here. Yeah. So is everyone cool with that? I'm gonna get rid of all of this. So we've established the bounds on the top half of our red area. The function then is 1/2 f of theta squared. What's our f of theta? Yeah, just 1 plus cosine theta. So we just want that theta to sweep that out. So we have our outer as the cardioid and the inner basically is 0. Okay, d theta. And so that's going to give us, since we doubled it, we're going to get both of the red areas when we compute that interval. So we're going to compute that integral and then add our result to the pi over 2 to get that the area of that beam. Yes. So we've got the integral from pi over 2 to pi. 1 plus cosine squared, we're going to FOIL or expand that out. So we have 1 plus 2 cosine theta plus cosine squared. Integrate each piece. So let's write, we've got our cosine squared, let's write that as 1/2 times 1 plus cosine of 2 theta. And antiderivative, we've got theta plus 2 sine. Plus 1/2 theta plus 1/4 sine 2 theta. And then actually we could combine the theta and the 1/2 theta. So we could say that's 3 over 2 theta. So we're dealing with less terms. So, plug in and have fun. It's 3 pi over 4 minus 2. These two are like terms. So the area we're after is that area plus half the circle. Pi over 4 minus 2. Questions on that?
On the test, are we gonna have an inner minus an outer? instead of it being like that.
Could be. You have two in your homework. Well, technically one. So it's not like you wouldn't have any exposure to that. Okay, last thing, pause this. So let's just, you have some homework questions too. There's 2 homework questions for arc length. But the point is we can find arc length and polar coordinates as well. Derivation, I believe, is in the textbook. But what we're looking at is the integral from a to b. Again, this is a theta value. Square root of theta squared plus theta prime squared, or r squared plus r prime squared. Let's find the arc length of the cardioid 1 plus cosine theta. Go ahead and put that graph. So we're going to find the arc length of that.
How would you know what to choose?
Okay, so how would we know what balance to choose? Honestly, when you're doing a lot of things in polar coordinates, symmetry is your best friend. Symmetry is utilized and more helpful way more often in polar than it ever was in
Well, I
rectangular.
get this, but you don't even have graphs. Like, how would you just?
Yeah, so like if you didn't have a graph, then you would just start plotting points and see how long does it take for this thing to be plotted in one full curve. So let's just accept for a fact. Let's just say that it was given to us a full curve. It's generated. For theta value in between 0 and pi. So let's just say we were given that. And r equals 1 plus cosine theta, that is our f of theta. So if we know the entire curve is generated from 0 to pi, we'll just look at half of the top, and then double that length. So let me make a note here. Compute the length of the top half. Now, notice with arc length, we're not thinking about like areas. What we trace out as theta varies from wherever to wherever. It's just that if the function or the curve is generated on f of theta from a to b. So we were given that the curve is generated from 0 to pi. So those are our bounds. We don't have to think about it's going from 0 to pi, right? Theta is 0, theta is pi. We don't have to think of it that way. We say the whole curve is generated from 0 to pi. So it's just really straightforward. That's our bounds. So the arc length here is twice the integral from 0 to pi, the square root of, I don't know how you want to write this, r squared plus r prime squared d theta. So we need to find r prime, plug that in, try to simplify that. Hopefully that comes out to like a u substitution or something we can work with. Yeah.
So if we're computing only one to the top half, should we be doing it for half of the thing? Instead of whole? Mean 0 to pi over 2 rather than 0 to pi.
Yeah.
But only we're given the top half of it.
No, yeah, it's 0 to pi.
Yeah.
But what's the
Yeah.
period of that curve? Like, is it
Let's
full one
check.
to 2 pi or pi?
Let's check. And I think it's from 2 pi actually. Yeah, so pi would actually give us that half. Sorry, I miswrote that. Thank you for noticing.
So if you did it from 0 to pi, then you just doubled it, right?
Yeah. Okay. Yeah. So 0 to 2 pi. My bad.
It doesn't matter though, it's not right if you leave it like that, right?
Yes.
It's not an equation.
Like this?
Yeah, that's how it works.
That's what I thought you were
So
questioning.
if we double it, if we didn't double it, we would integrate from 0 to 2 pi without the 2 there. So yeah, either way, it's the same thing. All right, so we'll find r prime or f prime of theta. Derivative of cosine. And maybe let's try to simplify this radical before we go off computing that. We can fit in what we have, but off to the side, let's simplify.
If there's a sine squared plus a cosine squared in it, can that be a 1?
Yeah,
Yes.
okay, so we have the square root of 1 plus our cosine squared, that's r squared,
I memorized 2 by
plus r prime squared minus sine
anyway.
theta squared. No, we'll just continue with this, I guess, it's fine. So we expand that once again, 1 plus 2 cosine theta plus cosine squared plus sine squared. That's where we're at. Sine squared plus cosine squared is 1. So then we've got to figure out how do we integrate the square root of 1 plus 2 cosine theta?
2 plus.
Oh, yeah, 2 plus 2 cosine theta. So this is 1, and we're going to combine it with that 1 right there. Yeah, that's what I would do. Honestly, I would take the 2, factor the 2 out, so that we have under the radical, we have 2 times 1 plus cosine theta, and then we can take the radical 2 out, and just try to determine how we integrate the square root of 1 plus cosine. So does anything help us here? Well,
Just take the antiderivative.
yeah, so what would it be though? How would we find the antiderivative of that?
We have 1 over 2, that. I don't remember.
No, because then you got to account for the derivative of the inside where there's no sign. Yeah, there's no negative sign in there. That's kind of the problem.
Is there a trig identity for that?
Yeah. Which one?
I haven't written it down yet.
We've seen it a lot actually.
Well, is it 1 minus 2 thirds?
Not that one.
Wait a minute.
Oh,
This identity kind of has a 1 plus cosine in there. once we look at this way, right? But going from the 2 cosine squared to the 1 plus 2 cosine of 2 theta rather, you just double that, right? So what would the identity then be for 1 plus the cosine of theta?
2 cosine squared.
Not 2, we wouldn't
Or
double.
would be 1/2.
Yeah, right, that's 2 cosine. So going from right to left, we have the angle, right? Oops. So that helps because it's a single thing that's squared, and we're dealing with that under the radical. So that's what we're going to use. It's 2 square root integral 0 to pi. Since we're going from, yeah, so we can actually have the square root of 2 and the square root of cosine squared. So the square root of 2, we have 2 root 2 times the other root 2, yeah, times the integral. 0 to pi cosine theta over 2 t theta. Yeah, so our constant is just 4. What's the antiderivative of cosine theta over 2? Right, 2 sine theta over 2. So we've got 8. Sine theta evaluated from 0 to pi.
Answer 8.
0, 0, yeah, 8. Okay, so that's the arc length
Oh, so it's just-
of that curve. Do you have any questions on 12.3? So let's talk about the content on final. Don't forget your note card. Everything but chapter 12, no worked examples.
Is it front and back or just front?
Yeah, front and back, 3 inch by 5 inch. So there's going to be 12 multiple choice questions. Yeah. One question from 6.2. Where you set up and evaluate an integral to find the area between 2 curves. One of those. one where you set up, evaluate integral for finding volume. Using the disk washer. Yeah, this one will be disk washer. But one of them will be disk washer, the other one will be shell. Sorry, one question. Same thing, set up an evaluate an integral for the volume using the shell method. There's one integral, evaluate a given integral. And, you know, this could be by parts. Yeah, by integration by parts, or partial fraction decomposition, tricks of. So you really should look at those cases and determine when do I use integration by parts or partial fractions or trig substitution. That way you can recognize which one you need to use.
What's the multiple choice?
They're, you know, like, I don't know, short answer. Like it could be like the equation, let's see, the equation r equals to 2 cosine theta represents what? A hyperbola, B a line, whatever. Those kind of things. Yeah, they're just varied. So the multiple choice is really just varied, you know, from chapter 6 all the way to chapter 12. No, I don't even think they're conceptual. They're very concrete. Yeah. I know that's vague, but I mean honestly, it's there's thousands of things we could ask. There's 2 questions where you're given a series. Determine if it converges or diverges. One question given a series. Use composition. And perhaps or multiplication to find a new series. And state the interval of convergence.
What do you mean by that?
So I'll write an example here. Yeah. So for example, given f of x equals to 1 over 1 minus x, or in summation notation, converges for absolute value of x smaller than 1. So if you were given that, let's say you were asked to find the series, an interval of convergence for x squared to divided by 1 minus 2x. So we have to first of all figure out how x squared over 1 minus 2x relates back to 1 over 1 minus x. So I guess kind of where we would start with that is we would say, well, this is x squared times 1 over, our x here, 1 over 1 minus x, but our x is actually 2x. So not only did we use composition and 2x in place of x, we multiplied that by x squared as well. So that's equivalent to the original series, k equals 0 to n. We had x to the n, where our x now is 2x. And we multiplied all of that by x squared. So I forget what numbers, you had a kind of a similar thing on the last test, towards the latter half, at the end of the test, rather. Okay, and since we replaced x with 2x, we would say that this converges with the absolute value, not of x less than 1, because x is now 2x. So the composition affects the interval of convergence. The only thing we had to ensure is when we multiply by a power of x, that the new power that results is larger than 1 for all of those terms. And since larger than 0 for all or equal to 0, 2 times x to the n times x squared is x to the 2n. So we would have a power of 0, 1, etc., etc. Sorry, 0, 2, 4. So really the only thing we need to ensure here is that the absolute value of 2x here is less than or equal to 1. And that would give us our interval of convergence. Sorry, less than 1. So just something like that, straightforward, but it also helps us build other series or other functions from those operations. Yeah.
Then that would be, that's what the interval conversion you'd say, we would value it like negative 1/2, less or less than x, less than 1/2,
Right.
you test those ones.
Yeah.
Is that right?
So yeah, here actually we have a theorem that guarantees that the interval of convergence is just from negative 1/2 to 1/2. So we don't have to test the endpoints. We tested the endpoints when we used the root or ratio test because they're inconclusive when they're equal to the endpoints.
They can't be versus, correct?
Do what?
They can't be, not all.
Yeah, it just depends on the original series that you're given. You have to just base it off of that. That's what I mean there. Start another page. You'll have one question where you have to find the slope of the tangent line. Just to review that. Find the slope of the tangent line at a given point. And polar, our theta. We did a few examples in 12.3 of that. There's one question where you're given parametric equations. You have to converge to Cartesian. Find the derivative of the parametric equation. which is that. So it just might say find dy dx. Find the derivative and the slope of the tangent line. At a given point. So that was from 12.1. Okay, and then one question finding the area between two polar curves. The graph will be provided. It's 12.3. Like I said, I think a good place to start is to just look over exams. In light of what we know is sort of on the final, just look over old exams, and then you can practice the problems on MyMathLab for those exam 1, 2, and 3 reviews. That's it. That's what's on the final.
Do you know how the points are gonna be distributed between the current unit and previous units?
No, not off the top of my head. I mean, I have them assigned to the questions. I don't have that. So, do y'all have any questions or other things you want to look at or talk about?
What hours do you have tomorrow?
What?
Hours for tomorrow? Or do you have?
Oh yeah, I have, but it's probably gonna be busy. Y'all can come in. From 1 to 3. Tomorrow, and then an extra office hour from 5 to 6 on Thursday.
So that's the only thing that.
Okay, well, I'll hang out for another 10 minutes. If you want to go, feel free to go. Whatever we do, I'll post on D2L. Yeah.
I never know my first exam back. Still have that?
No, I totally threw that away. I still have it.
Oh.
Yeah. I have all of your exams if you haven't picked them up. No. Golf stuff for that.
Did I get my exam?
Yeah, they're all in my office, so you wanna back up?
Sure.
I feel better now that I
I'm just gonna make sure no one else
I was
has any
like half
questions.
vomiting when I was going through every single note section. And I'm sitting there like, this is twitching by myself.
Hey,
I do.
I was wondering how exactly you rate those, because I know some.
My aunt is like, you now, but she's not. But like, I study this all day.
That's valid, but it also counts. Okay. So regardless of the score, it counts. At least once. You know, if it counts twice, if it's better.
Okay, so like hypothetically,
No.
if I did so
No, hypothetically, you did something, you just gotta see the final. Every part of your liver needs to happen.
It's not that bad in the most.
You wanna see what happens?
Like, not remember
Sure.
everything you need to
You're an
remember.
automatic application.
I thought that I would, yeah, I thought I would really.
Do you have time Wednesday, 1 to 3,
Yeah.
Thursday evening, 5 to 6? I guess it'd be a week by Thursday.
Yeah. No, I mean, might as well take a glance before it starts.
Yeah.
I'll be around. I mean, like, it kind of fluctuates between sometimes being not so bad, and sometimes I just pretty close to death. I told you that was gonna happen, like 12-1 and 12-2, I was like, I was looking at his notes, and I was like, well, I mean, it wasn't quite like he beat him with a stick.
Yeah.
How that goes.
I really
They're
don't
just
like.
crying myself to sleep.
Don't like it.
Everybody's creative.
Yeah, how does the final server work as far as grading goes?
So it has to count once. It can count twice if it's better.
Wait, what?
It can count twice.
It can count twice if it improves your grade. Okay, so
Wait, whoa,
That's
so
where
if
you're
you
at.
take
I
two
haven't,
exams?
Well, regardless, it counts as one
so I
exam,
haven't
and
calculated.
if it
the
can,
homework
increases your
quiz.
grade,
Here,
it'll
that's
drop
where
the
you're at.
level. And replace with
Oh,
final.
okay.
So you'll have
Okay,
two
so yeah,
finals
we just-
and three exams.
You got it.
Yeah, of course I gotta take it, I'm just like.
Yeah, some people are fine just passing, other people
Yeah.
need different grades for different purposes.
Okay, cool. Thank you. It's like, yeah, like, it'd be like an 85 or something about the transfer.
Yeah.
Now you guys got it. I don't need to
So-
read this, I got it.
Just a basic calculus question, I guess, because like, I was under the misinterpretation, I guess my physics teacher told me I was dead wrong for thinking this, that these, where I was. So this is what, this is f of x, 2 minus f of x, 1 over x2, that's what delta x is, right?
Yeah, delta x over delta 1. Delta y over delta
This-
x.
Yeah,
but
that's
this
delta,
means-
that's changing delta y over delta x.
Oh,
That's just delta x.
oh, okay, okay. Okay, so all this means, really what this is saying is that the infinitely small number, right?
Right.
Right, so means infinitely small number basically, which is why when we,
Linear measure.
which is why when we're taking an integral, it's basically like small rectangle, at least with respect to the x-axis, so an axis not theta. It's saying that's basically infinitely small widths of
Yes.
rectangles, because it's more of an accurate measurement of area, just like Riemann's thumb, but very like, it gets more accurate, the more the narrower, more rectangles,
Yeah.
right?
Yeah.
I know that's like a basic, I'm just
Yeah.
kinda.
No, there is a difference.
There's a huge difference.
Yeah, and then when we look at, this could be like if we look at function values, y values, we could say this is equivalent to like the change in y, the exact change in y. This would be the differential, which is equal to that line of x, x. And so from this, it's just this came from the change in a linear approximation to a curve point. And you see from that that's dy over dx.
How do you know, like, when to use limit comparison
Versus direct comparison. Honestly, I would always just use limit comparison.
Yeah,
Really?
you
I
can't-
wouldn't even think about the direct comparison.
Yeah,
I mean,
because
if
it
taking
rarely
a function
ever
is
works. Because it
painful.
rarely ever
What
works.
if you say on the test?
He doesn't.
Well, yeah, then you have to use it.
So it's,
Do you say anything
But
that's
if he doesn't specifically tell you, then never use it, just use the limit
Yeah.
comparison.
It doesn't specify.
Okay, so, cause this, the limit of piece of k over h, case of k, right?
Yeah.
Is less than any greater than or equal to 0, right?
yeah, A over B.
Is a over b?
But you have to pick something that's always gonna be.
Yeah, okay, so you still have to use the comparison, so,
Yeah, but we don't care which one of these is larger, because that comes out in the limit. So we don't, which one of these is smaller or larger, it doesn't matter. What the limit is and what B does tells us everything.
okay, so
Or-
that was, like that 1 over, 1 plus 2 over, 2 over to the k over,
Yeah.
1 plus 3 over to the k over.
That one.
Yeah.
I would
Use
use
limit.
line comparison as this one.
You
I
just
would
pick
say
those two.
Limit comparison was.
Because,
Which is,
yeah, convergent geometry.
so,
And
Am I wrong about limit comparison, or you?
I do-
Wait,
why
wait,
is
no,
that
you
yield
do
two?
find, you do find a piece of K, because so so which one am I thinking? I must be thinking the ratio where you just say it's a sub k, and then you pick an a sub k plus one, and you
Yeah.
divide this by this.
That's
Plus
ratio.
one over.
Okay, yeah, so this is the one where you divide the original by your comparison.
Yeah.
Got it.
Right, right.
Let me see that.
So that's a finite limit, which means these two things grow at comparable rates, which means that this is comparable to this converges
And they have,
comparable to this.
meaning they have to, they multiply at least the first term to multiply to the same factor.
Right.
Exponent.
Yeah. So it could convert, like, A could be like, as infinity, A could be the sequence or a series with A, the sum could be approaching 4, B could be approaching 2, right? They're really close to comparable value.
What is it, as long as it's not infinity, right? It's infinity, then it's inclusive.
Well, if it's infinity and B diverges, then A diverges. If it's 0 and B converges, then A converges. If it's finite, it'd be the same.
Okay, so how did you get to?
Oh, I don't know if it was 2 or not.
I
think.
Oh, yeah.
We both do the same thing. I'm like, BS, that's two. I don't
I
believe
think it
you.
was 1, actually.
Okay, yeah, so I just did it.
Yeah.
So these would go with.
So finite limit that's not 0 means these two be the
Wait,
same.
I'm sorry.
Finite limit that's not 0, mean that these two series do the same thing, and since we picked this.
Converse them at a sub k.
And the
So
number,
if
the
it's
number,
zero,
the finite number is literally what they're raised to, right?
Yeah.
If it's 0, then what's up?
If it's 0, B has to converge, then A converges.
So it can't be 0.
It can't be 0 if the thing we chose converges,
Okay.
then A converges. If what we chose diverged, and the limit is 0, then it's inclusive.
If it's, okay, so if p sub k is greater than a sub k, and diverges, that means a sub k diverges, right?
Because if this is the
That's
base greater,
part,
right, and A diverges.
Yeah,
Yeah.
or saying, or this diverges, because this is the one we picked, right?
Yeah.
If this diverges and it's greater than this, then we know that diverges.
No, because we know the series that's given, this is direct comparison. The series
Oh,
that's given
right.
is smaller than the divergent series, still means it could converge.
Okay.
So in order to diverge, you have to be larger than the divergent series.
Like, if it's divergent, it's gonna go to infinity. If it's less than infinity.
Oh,
Is there gonna be,
Okay.
is there gonna be a question about direct comparison?
Didn't look like
I
what you
really
said
don't,
at all.
honestly don't remember.
It's like, it
I
didn't
wrote
look like
two
it.
finals.
Those two are the worst in text. I hate those.
Yeah.
Looked like you couldn't say so.
Always said use.
Well, multiple choice question,